So on page 32, we're going to acknowledge the inherent reality that I'm sure some of you have been thinking about as you've been watching this series of videos, which is, Herbert, if we're dealing with curvy shapes, why in the world are we using boxy rectangles? It doesn't make sense to use a boxy shape, like a rectangle, for something that clearly has this sort of angular look to it. And that is true. That if we really think about it, and this was kind of what tangent lines were all about in our first semester together, when you really look at the distance between 2 points on a curve, it doesn't really look like it's too curvy by the time you zoom in. I mean, I'm going to zoom in to the point where it's practically imperceptible what I'm looking at anymore. If you didn't know any better and you were just looking at that diagram, only those 2 points with that little bit just kind of connecting them, you'd swear it's a straight line. And if I did that for any points, if I looked here, still looks like a pretty straight line. And it's only when we zoom out, and even then hardly perceptibly so, that we can see the curvature start to take shape. So if we're limiting ourselves to only geometry, meaning only curvy shapes, it does stand to reason, why aren't we using shapes that have more of an angular look to them? Why aren't we using triangles or trapezoids or things that aren't necessarily four right angles put together? So in page 32, we're going to try to attempt to kind of use a non-traditional shape. This is where Riemann actually sort of falls off. Riemann limited himself to only rectangles, and you'll see his name only associated with left, right, and midpoint because he only did rectangular shapes. This fourth method is actually going to be called the trapezoidal method, but it's not actually called a trapezoidal Riemann sum. Riemann never did trapezoids. Other mathematicians were the ones who sort of acknowledged that angular shapes might be better than rectangles. So when you hear Riemann sum, you're only going to think rectangle, which is kind of easy to remember. Riemann starts with R, rectangle starts with R. And then when you hear trapezoid, you'll kind of know it's sort of in a fourth category all on its own. So in question letter A, in number 4, it says partition the area under the curve into 4 trapezoids. Now, if you're thinking about this and thinking about where a trapezoid would fit best in this diagram, I'll encourage you, if you can, to think a little bit less traditionally about trapezoids as you might be picturing them. Most people picture trapezoids, and rightfully so, as the shapes that we learn in geometry, specifically shapes that have a parallel top and bottom, and then sides that sort of angle in different directions, like the Pizza Hut logo, for example. Whoop, it's going to decide to zoom. There we go. Now, that is a trapezoid, and I'm sure that many of us are pretty well conditioned to look at a trapezoid and to see the base 1 and the base 2 and the height. We might even go so far as remembering the area formula for a trapezoid, which is 1/2 base 1 plus base 2 times height. All well and good. All of that is great. The problem is this shape is not quite compatible with the spatial orientation of this graph. So what we're actually going to do is create a slightly less traditional trapezoid. And I'm going to start in the middle of the diagram, which might seem like a kind of random choice, but I'm choosing to start here so you can see the trapezoid in its full glory. I'm going to start with the trapezoid between points, or x coordinates 2 and 3. Now, using my ruler again, I'm going to create the heights first, and I'm actually using that word a bit misleadingly. These are actually going to be the bases of my trapezoid. And it might seem like I'm making weird choices right now about the choice of words, but take a quick look, if you can, just by making those two heights at the resulting shape. It might not seem like I've made much of a shape yet, so I'll try to define the edges a bit more clearly with a highlighter so you can see that by connecting those 2 points with a diagonal line, and notice I did use a line, but again, when you're talking about such a tiny space on a curve, it's practically linear anyway, you can kind of tell that the trapezoid is starting to take shape. And if you're looking at it going, no, 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 that can't be right. The top of it is supposed to be parallel to the bottom. I'll encourage you to literally turn your paper, as you'll see I do here, in order to see the trapezoid truly take shape. If I highlight that fourth edge, you can hopefully see it now. These are going to be trapezoids that are going to be situated so that the vertical dimensions are actually going to be your base 1 and base 2. The height is going to be the distance between the x coordinates. So I'll just label this hopefully clearly so you can see those two values. The height is again going to be this little segment here, and the base 1 and base 2 are going to be defined by these edges connecting the curve itself down to the x-axis. So it might help actually to do trapezoidal problems sideways like this if your brain is really locked into seeing trapezoids as just that style of shape, where the top and the bottom are the parallel edges. If you don't have any trouble seeing this as a trapezoid as well, where your bases are vertical and your height is horizontal, then of course do the problem whichever way makes the most sense spatially. But this is the area that we're going to try to calculate. So I'm going to do the first one just so you can see how I'm doing my calculation, and then I'll encourage you to follow along with me as I draw the rest of the trapezoids and do the rest of the calculations. So let's, just for the sake of reference, stay a little bit rotated here, just so that way we can kind of see it. Now the area formula, as I mentioned, was 1/2 base 1 plus base 2 times height. So now I'll need to kind of look at this carefully and say to myself, okay, what are going to be these values in the context of the graph? Base 1 is the distance from the x-axis to this point here. Now, if you have your y-coordinates on previous pages, you might want to transfer them over. You can actually kind of luck out. The graph is pretty close here. So I know that this y-coordinate was 5. So that means the length of my base 1 is 5. Plus base 2, which happens to have a y-coordinate of 10. So that means the base length must be 10. And again, the formula for a trapezoid is 1/2 base 1 plus base 2 times height. So now I need to multiply by the height, which is, again, in this context, the distance from 2 to 3, which is simply 1. So now if I do that calculation, I do need to follow the order of operations. So 5 plus 10 is 15, times 1/2 is 7.5, or 15 halves, depending on how you want to write your answer, times 1 is going to remain 7.5. So there's the area of my first trapezoid. Now, I'll need to repeat this process for all of the other trapezoids to fill in the rest of the region from 0 to 4, since that was the specified interval in the original problem. So I'll do another one just so that way you can see where I'm getting this from, and then I'll ask you to do a couple on your own for practice. I'll now, just for the, again, sake of clarity, do the trapezoid from 1 to 2 so that we can see it. And if you have the ability to color code these like you see I'm doing here, it might help. Some people find this to be an unnecessary step, but some people find that the visual of seeing the trapezoids and seeing the different dimensions can really help them. So use your best judgment and just decide what's best for your eyes. Now, of course, again, if it's best visually to rotate the paper so that you can more clearly see your base and base, that's a good idea as well. Now, if you're looking at this going, oh, wait a minute, hold on, I already know one of these bases, that's actually one of the main advantages to the trapezoidal method. So you actually end up reusing one of the numbers. This base 2 of our green trapezoid is the same 5 that we were using in the previous one, so that's kind of nice. The only base I don't currently know is this one up at the top of my trapezoid, so from the x-axis to this dot here, and just knowing my coordinates, I already know that that y-coordinate is 2, so that saves me some significant time. Again, the formula is 1/2 base 1 plus base 2 times height. So I'm going to use 1/2 times base 1, which is 2, plus base 2, which is 5, times the height. And again, don't forget the height in this context is the distance from 1 to 2, which is 1. And again, I'll just do that quick calculation. 2 plus 5 is 7. 7 times 1/2 is 3.5 times 1 is still 3.5. Now, of course, it does get a little bit of, it gets a little bit tight to try to measure in this tiny little area and show all of your work. So you may want to consider an easier, maybe like table of values, or use some scratch space on the side in order to do the calculations and the areas for the last two trapezoids. You're now on your own to do the trapezoid from 0 to 1 and the trapezoid from 3 to 4. So draw carefully. And don't forget, reuse the y coordinates from the previous page because you're going to need them for the base of this teeny tiny little trapezoid over here at 0 and the base way down here that takes you all the way from the x coordinate 4. So I'm going to stop this video temporarily to give you some time to work, but the goal right now is to try to finish these trapezoidal areas, find the sum of those areas. That'll take care of part B. And then in letter C, to use your observational skills. What do you notice? How does this compare with the left Riemann sum, the right Riemann sum, the midpoint Riemann sum, and the true area that we found way back on page 29? Hopefully by the time you did that, you can see which method, if any, clearly seems to be the superior method for accuracy, versus which method or methods seems to be superior from an efficiency standpoint. So consider that as you're comparing. There's accuracy and then there's efficiency, and both of those things are equally valid here. So consider that as you answer question letter C. And in question letter D, try to anticipate, why do you think, despite its relative accuracy, the trapezoidal method might not end up being a great choice? Again, think of our two criteria, accuracy and efficiency, and keep that in mind for question letter D. So in the next video, we'll talk about number 5, and hopefully by then you'll have finished the trapezoids, gotten a bit of a technique down, because in question number 5, we're going to use all of our techniques, and the goal is, by then, to have a sense of which one is going to be accurate, which ones are going to be easier, and how to make sure that you can do them all efficiently.